And I guess I should share my screen. All right. Let's kind of move into perception, learning, and inference. We'll briefly review learning styles, look at some open source data sets, cover some neural networks, look at Python as a language real quick. And because I don't think you're going to need to do a lot of sophisticated stuff in Python, because we're going to rely on machine learning frameworks. So other people that have developed these frameworks have done a lot of the hard stuff, and we're going to kind of operate at a higher level. This is not going to be a full-on machine learning course. Some of you all are in a machine learning course, and I'm sure you're learning the theory, you're doing proofs and that type of thing. We're not going to do that. We're just going to present some concepts and that type of thing. Again, this is a course that's really dealing with the system of systems, right? The system of subsystems, perhaps, but it's a lot of different technologies. So yeah, we kind of skim over them a little bit, right? My presentation may be a little different from others. That's okay. There's a lot of different ways of looking at these things. If you've had Python before, if you worked with it before, great. Hopefully I won't waste too much of your time. But if you haven't had Python before, don't panic. If you are needing to do some work in Python and you're struggling, we'll get you there. Okay. So, all right, let's first look at learning styles. They're generally grouped into three different techniques. Supervised learning uses these days, typically large, very large, extremely large data set where we have sets of inputs and that are provided along with the expected results, also known as labels. Right? So this could be tabular data that says, all right, for loan approvals, we're going to collect certain information about a person's current income, their expenses, their credit rating, maybe some other factors, and what their history has been on paying off loans in the past, right? And that would be kind of the results, and we would, or you might do that based upon like a human rater would do, right? So you've got this data set. Hopefully you've got lots of them, but they have both kind of the questions and the answers, or the inputs and the outputs of the system. Then we also have unsupervised learning. Here we use lots of data, but we don't necessarily have the answers, right? The labels. We've just got lots of different datas. And we can use these, though, still to find trends and clusters and that type of thing, but without the specific answers a priori. We're not going to talk a lot about unsupervised learning specifically. We're going to focus on supervised learning, and we'll talk a little bit about reinforcement learning, assuming we have some time. Reinforcement learning now uses many trials or experiences. These may be collected in real life, but oftentimes in a simulator. And we're going to use those to explore how best to solve a problem. So AlphaGo, and the type of thing is kind of a famous example of reinforcement learning. These days, doing a lot of different video game type of solutions in reinforcement learning. These are maybe not the end goal is to win at a Go game or a video game, but they're very convenient ways of testing out algorithms. But reinforcement learning is that experiential. So we're going to explore and learn as we explore. Sometimes it's going to work, and sometimes it's not going to work. We got to make sure that we don't kill people in that process. So we have to be aware of the limits of reinforcement learning. So, but yeah, we'll first look at supervised learning, and we'll spend a few lectures on this. Now we have here a data set with lots of different inputs and correct outputs. Right? So as correct as we think we can make them. And then we're going to adjust our model to predict the correct outputs given the inputs. Right? So we're gonna have some sort of model here. It might be a neural net, might be something else. Right? So lots of different other types of models. If you're taking a machine learning course, you're going to be studying support vector machines and all sorts of different techniques, decision trees, random forest, all fun stuff like that, right? We're going to focus on neural nets. And so inside this box is some sort of model, and we're going to provide our inputs, and that's going to, at any given time, going to produce some forward predictions, right? So we might take, we might have a data set with 1 million different examples in it, right? So we're going to put each of those 1 million different examples into this, and each of those examples might have you know, anywhere from a handful of inputs to many inputs. Computer vision, we're typically dealing with pixels and an XY type arrangement or point clouds or something like that. So our inputs can actually be huge in terms of dimension size, right? And for each of those, let's say, 1 million examples, we're going to create a prediction with our model. We're going to compare that with what we know should have been predicted, right? And that's that correct output. And then we're going to somehow adjust the parameters of this model in order to fit it to that data, so that now when we put data in, it predicts something that very closely aligns with the correct outputs. We're going to typically do that in an iterative way. It's just not possible with these large models to come up with some closed form solution to just calculate them. So we're going to do this kind of backward training updates where we look at how far off we are and try to predict how to change those parameters to improve those predictions, right? So there's a little bit of an optimization process going on here, right? So we're going to iteratively optimize the model, typically using derivatives of all these functions in here that are involved in this model, right? And by looking at the derivatives of, let's say, a cost function that is describing how close or how far off we are here, then we're going to figure out how much and what direction to tune any given parameter, right? So, so we'll see neural networks have weights associated with different connections and between neurons, right? And we're going to update those weights. There's some biases also that kind of scale things up and down. and we're going to need to adjust each one of those weights. And in some of these very large models, there's millions of these things, right? And so we need some sort of disciplined process to figure out how to optimize the changes in those parameters so that we converge upon a model that is accurate, minimizing the error between predicted and a correct output. So that's supervised learning. Yeah, I introduced a little bit of thoughts of neural nets with weights and biases in there. But again, the idea is that this is generic. If this is some other model, doesn't have to be a neural network, but we're using the same type of optimization process to try to create this or tune this model so that it is providing the right outputs. So we call this supervised because it's kind of like there's a teacher there that's saying, nope, that was a little bit off. You didn't quite get the right answer. Try again and keep iterating at it. All right, so more on the other, in particular, reinforcement learning in a few lectures. But so we need data in order to do this, right? So we need these training data sets that have all these different inputs and have these correctly labeled outputs. So here I've listed a bunch of these different sources and that type of thing. The Kitty and Cityscapes are kind of the big ones. There's some others here that are included. These may change over time. I found this data set listed somewhere. I can't remember whether it was a book or some other reference, but it turns out it was a little bit out of date, but I did find I think the same data set in Kaggle competition, so it's stored there. So if you're doing your project in this area, I would strongly encourage you to use a relevant data set. Go ahead and pick one of these. Actually, let's go and look at the Kitty data set, and let's see. Okay, so here, this was collected. It's going to talk a little bit about how it was collected, when it was collected, where it was collected, and then give you some examples. So here they have a stereo camera rig up here, both mono and color. They've got a GPS, and then they have this 360 degrees Velodyne laser scanner or LiDAR there, right? So, and here they can. So they drove through this area. Do we need all that noise? I don't know. Just skip over some of that intro there. This line is just as between the cameras there. Let's get a little bit here. You can look at this on your own. There's some segmentation going on there. Okay, so just some information there, and okay, where are we at here? All right, so encourage you to go click through these. You may download some of these and take a look at them, open them up, look at how the data is arranged, stuff. So in machine learning, it's typical that we would have one or maybe many files where each file has comma separated values in them, and kind of looks like an Excel data sheet or spreadsheet that's been saved, the data part of it, right? And so you're going to have the fields going across in a line. If it's in clear text, then it's going to each input is going to have its field and separated by commas, and then you're going to have labels associated with the outputs, and that depends upon the problem we're trying to solve, right? And that problem may be a classification problem where you're determining that oh, that's a dog, a bicycle, a car, a truck. That's a classification. You're classifying it into these different object type classes, right? But you probably want more information than that. You want a object detection, where we'll get into that in later lectures, where now we want to know not only what type of object is out there, but where it's at in that image, in a computer vision type application. And we can relate that to a model of real space in terms of some sort of coordinates relative to a reference frame. And that bounding box is going to typically, the location is described as a bounding box, which is usually a rectangle that is, as best as our labelers can do it, or as best as our model can do it, describing the extents of that particular object. So if it's a bicycle, it's or a bicyclist, then the top line of that object or bounding box is going to be probably the top of the helmet of the rider, and the bottom is going to be the wheels, and the left and right are going to be the let's say back end of the rear wheel, front end of the front wheel. Of course, that's assuming we're seeing it at a side or profile type view, and that's not always the case, right? So one of the aspects to these data sets is that they should include lots of different examples, but those examples should have some diversity to them, right? So if we're trying to look at bicycles and classify those, we need all sorts of different bicycles, and maybe kids' bicycles, maybe a triathlete's bicycle, maybe an e-bike. Maybe those don't have a whole lot of difference, but we're going to see, we might observe one, again, end on, from the back, from the front, from the side, or at oblique angles, and or it might even be crashed on the road in front of us, and we need to avoid that. So the more diversity we have in these data sets, then the better we can train our machine learning models. Okay, let's start to look at neural networks now. And neural network is going to include weights that are going to control how much influence each input has on a particular neuron, right? So neural networks are composed of many neurons. They're modeled after our understanding of the human brain, or simplified versions of those. So we have all these different neurons. These weights are control the strengths of these connections between them. And you can think of those as synapses if you've taken a little biology and studied that. I hope you've had some exposure to that. There's also a bias term, right? So we can add an offset to the sum of the weighted inputs. Each neuron has one or several inputs to it, and each of those inputs are coming from different other neurons, probably in a layer before it. We'll show a little bit more of these. And each of those synapses or connections can have a unique weight associated with them. And then we might just find that our models train better if we add or subtract a bias to that whole amount, right? And these are all summed up and then added to, the bias is added to them. Then there's this activation function. We'll look at this in detail. This is a nonlinear function that is applied to the combination of the signals that are weighted, the signals coming from previous neurons that are weighted, and then the bias term added to them, right? So that's going to provide some value. Then we're going to run that value through this nonlinear activation function, and that's going to be the output of that neuron. And then that neuron may go to other neurons, or it may be an output neuron. We're going to train this via back propagation. So I hinted at this earlier slide where I'm saying the supervised learning, we're comparing the outputs, we're coming up with some measure of how well they predict the correct outputs given the inputs, and then we're going to take that information and kind of move it backwards through the model to try and update those parameters. So here we're adjusting the weights and biases to match the results that the train set says you should have. So what is this neuron? Well, we don't, this is inspired by what we know of the neurons in our brains, but they are an artificial concept, right? So don't try to read too much into that. But what do we have here? This neuron here has 3 different inputs, x1, x2, x3. Might be 1, might be many. If it's 0, it's kind of like not doing anything. It doesn't need to be there, right? But sometimes we actually do that, but that's a more advanced topic. And but typically you're going to have 1 to several and inputs. These are then signals from either our inputs or our previous neurons. And so each one of these would tend to be normally a scalar value. And then that value or signal coming from a previous neuron, its output, is going to be weighted by these weights here, right? And then they're all summed up, and then there's a bias term added to it. So we could draw yet another connection here that represents this bias term. We don't tend to draw it just because by the time you put these things in a network, it just gets too messy. But just understanding that that is possible there. Then we run it through, so this equation here produces Z, and then we run that through our nonlinear activation function, and that produces our output, right? So here in mathematical notation, we've got our X. Now X here is a vector, so's W, right? So we'll take the transpose of this, so as we multiply the weight vector by the inputs, then they're going to sum up. Each individual weight is going to be multiplied by its corresponding X value and then summed up, right? And then plus a bias. So these are vectors. That's a scalar, and because we're summing all those up, that's going to produce a scalar value there at Z. Then we put this through a nonlinear function, and that produces our output, right? So, all right, I think I covered all those things. So now we take all these neurons and we organize them into layers, right? So here, this is kind of a canonical or classic layout of a neural network. This type of technology goes back to at least the 80s. And I think maybe you can trace it back to even a few decades earlier than that. I'm not going to be a historian here. So, but we have an input layer, and we'll have some number of these. Again, it might be tabulated data, and this could be income, credit rating, where they live, or something like that, right? And or it could be a computer vision where this is pixel 1, this is pixel 2, pixel 3, all out of some 2D array, or these could be points in a point cloud. And but these guys are going to supply values to neurons in a hidden layer. Right? Now, hidden here means that it really has no representation in the training data set. We've got input data, that's in a training set. We've got output data, that's in a training set. The output layer produces those output values, but the hidden layer, or in more modern deep learning applications, there's many hidden layers. These things don't have values in the training data set, but we're going to transform our inputs to our outputs using these hidden layers. So you see here we have these connections. Again, we can think of these as synapses, but this input value will be provided to each of these neurons, and each of these connections then is going to be weighted, right? So, and this input value is provided to all those, this input value, and so on. Then these neurons do their things, and then they supply to the output layer. And the output layer does its things and produces some sort of output. That output might be some sort of binary, like a classification. This might map to cars, pedestrians, bicyclists, and we would want this to be an explicit decision. That's a 1 if it's a car, and 0, 0, or 2, or this one's a 1 if it's a bicyclist. A lot of times we don't want to be so blindly certain about things, right? So we will construct our outputs to take on probabilistic values. And so now we might want all these to sum to 1 as a probability distribution, but A might be, yeah, I'm 90% sure that's a car, but maybe 7% that it's a pedestrian and 3% that it's a bicycle or something like that, right? So this would be 0.9, 0.7, 0.3 values that they're emitting. And we would want to train an output layer, or maybe typically we'd have, one more layer out here. We would kind of train these layers, and then we'd have maybe what's called a softmax layer out here, or something like that, that would produce some probabilities for us. And or we might want to do regression. We might want to predict speed of something, or something like that, right? So a value that could take on something between 0 and 100, or 0 and 120, or something like that, right? So we might do regression. Several other types of forms. It's not like an infinite number of different forms, but there's various different forms here, as you're probably starting to experience in just using machine learning models, whether it's ChatGPT, might be a whole sequence of words being emitted, that type of thing. All right, so activation functions. So I mentioned that. What are those? Well, first of all, I said it needs to be nonlinear. Well, if it's linear, what happens? Then basically you could kind of combine all those different layers together, and they would change, but you could just kind of collapse all those layers of some deep neural net into a single layer, and you basically haven't done much then, right? So by making these things nonlinear, now we get a lot of richness in our calculations. Again, if you're studying machine learning, you're probably going to, as a course, you're probably going to look at this theoretically and prove that that has to be nonlinear. But I'm going to ask you to trust me on this one. So for binary classification, we probably want it to reflect the probability from 0 to 1. So their activation function is going to either range of output values from 0 to 1, or at least be able to be easily scaled to that range, right? So that it can be used as a probability predictor, right? Training and that back propagation training process, we're going to want derivatives of things, and so that should be easy to calculate. So all right, so I'm going to run through a few different examples. We tend to study this logistic function or sigmoid function initially if we're doing a rigorous machine learning course, and even before we introduce neural networks, we'll look at a neuron that's just using this logistic or sigmoid function. And it's kind of the classic canonical one. We don't tend to use it as much in neural networks anymore. It used to be used widely, and it can work. It definitely does work. It's just we found better ones, but we still study it for its historical reasons. So here it's 1 divided by 1 plus e to the minus z, right? So this activation function is going to be this sigma of z. And so the nice thing is that this, if you plug in really small or numbers of z, or I should say large negative numbers of z, then we're going to take a negative number that's going to be positive. E to a very large positive number is going to be a very large number, but it's in the denominator. So when we take 1 divided by a very large number, it's going to be close to 0. Right? And on the other side, if we plug in a large positive number, it's going to be negated. So it's going to be e to some large negative number, which is going to be close to 0 itself. So 1 plus a really tiny number is going to be approximately equal to 1. So we'll have 1 divided by 1, and that's 1, right? So we're going to move from 0 to 1, but it's this region that becomes interesting, right? So we're going to cross through the 0.5 mark at z is equal to 0 here. And we've got what kind of looks linear there, but it's very nonlinear, very nonlinear. And when we look at this overall curve, it's very nonlinear. So this is really useful for mapping binary classifications. We can map 0 to false and 1 to true, and tough thing. So the derivative is tiny but non-zero at large absolute values of z. So we don't want the derivative going to 0, because then we won't be able to effectively optimize in our optimization process. All right, so that has some advantages, but hyperbolic tangent function has some interesting behaviors here. Now, instead of going from 0 to 1, we're going from -1 to +1. So this is actually a shifted version of the sigmoid function. If you put in tan h, and if you represent that in terms of exponentials, then yeah, you can derive these two as shifted. Derive one from another by accounting for this shift here in the scaling. Instead of going from 0 to 1, it's going from -1 to 1. So now here we have values from -1 to 1. That is effective in hidden layers because now the mean of that data can tend towards 0, right? So we're not going to be, we can account for negative values and positive values. We're not just trapped within this range of 0 to 1. So the 0 to 1 is kind of nice for the outputs, but for the hidden layers, we find that it's nice to have this mean balanced around 0. And again, the derivative is tiny but non-zero at large absolute values of z. All right, so now rectified linear function is kind of become a much more dominant one in recent times. And here, actually quite simple, right? So for values of z less than 0, we're just going to map it to 0. And values of z greater than 0, we're going to call that z, right? So here at z is equal to 2, we're about at 2 right here, right? So z is equal to 10, we're at 10 right there. So we just call that max 0, comma z. Trivial derivatives, derivative here is 0, the derivative here is 1, right? The derivative is a slope. And so it's super easy to calculate, very, very efficient calculations here. Yeah, the derivative is technically undefined here at 0. This is not a continuous, a smooth function. So, you're very rarely going to end up with values at exactly 0. So you can make some approximations there and just kind of assume either 0 or 1. It can handle values, produces values from 0 to z. It's gained a lot of popularity in both research and implementations. So a slight revision on that is the leaky ReLU function. Here we can provide a finite derivative for z less than 0. This is potentially superior to ReLU in practice, and this way, if you do have values here that are negative, you've got some finite derivative that can push your solution towards in the optimization process. We haven't talked about that yet, but we will. So it's potentially superior. How much is it used in practice? I don't know. It's debatable. So the improvement is marginal, but you may run into that. All right. So as we talked about, we have this training of neural networks. For supervised learning, we start with a data set with inputs and answers or labeled results. We train that neural net to produce the correct results when presented with the inputs. This requires now adjusting the weights and biases. And if you've done some optimization work in a mathematics course or somewhere in your master's research or something like that, you may have, or actually in a computer science course, right? So you may have looked at gradient descent as one of a very common type of approach towards optimization of a parameterized function. right? So it calculates derivatives of each layer and applies the, I guess I didn't prove this slide very well. I think I have more information on this in a couple of slides and some crude diagrams that try to help explain that. So, all right, so there's a number of different things that come into play in doing this whole process. One is, so we talked about the neurons themselves and how they have this activation function. We looked at those, but now we're going to introduce this loss function, and that's going to quantify how close the output matches the correct results. Right? So there's a number of different forms of these, and some are better than others. We'd like what's called a convex function to avoid getting stuck in local minimas, or for that gradient descent optimization function to work. If you haven't seen what's defined as a convex function, that's fine. Don't worry about it too much. Maybe I can draw an example here in 2 dimensions. You've got something like this that's pretty close to a convex function, in that if we go from here to there or here to there, we're going to stay inside the boundaries of that function. As a counter example, I'm not, the math department would hate me for doing this, right? But here, if we're moving from this point to that point on this function, then we're outside of the boundary of that function, right? So of the area that's transcribed by that function. So this would be non-convex. We want something like this, right? So, and I'm just kind of stating some of these things, just like I'm going to give you this loss function here without, going into tons of details on why or whatever. I'm giving you a little bit of motivation, but this is a classic loss function. And here, y hats are estimates, y's are labeled data. And we're going to have this loss function that is comparing the estimated, so what the model is estimating, with the quote unquote true values. And yeah, we're going to use that. We'll ultimately need the derivative of that. So again, if you want to, you can work that out, but you'll end up with this. If you take that with respect to y, you'll end up with this equation here. So, all right. Now we're going to, so that would be for like one instance of training data, right? So you have one set of inputs and one output, and then you have one predicted output, however good your model is at whatever iteration we're in. It's going to predict this y hat value, y caret, and that's going to be for a single instance of your training data. But you probably have millions of instances of training data, right? So, so the cost function now is going to sum all those and over m of those, and then divide that. So we're basically looking at the average of all of those, right? So, and this tells us basically how good our model is doing over the whole data set, right, for our weights and biases. All right, so here's my slide where I go into gradient descent a little bit more. And so it's a mathematical optimization algorithm. It's used, it's a generic technique used in a lot of different areas of optimization. So if you do like operations management or something like that, you'll run into this quite a bit. But the key parts of it are it's iteratively seeking a local minima by moving in the direction away from the derivative, right? So let's look at this. Here's some sort of function, right? So it might be, just only empirically known or something like that. It might be known. This is just in one, parameter, one dimension here. I'm calling it W. We know that W here, might stand for our weights, and there's like thousands or millions of weights in a neural network, right? So, but we're just looking at one here. And so let's say we start here, right? If we just randomly pick some values for all our weights and biases, and we start off this optimization process, and we plug in each of the inputs of our data set, and we collect up all of our different predictions, outputs, and we do that, for each training set example, calculating the loss, and then averaging all those for the cost function, this J value. Then let's say we end up right here, right? Again, this is a trivial example here in just one dimension, or in dimension in one W here, but we're right there, right? And that's all we really know. We don't know all this other stuff, but we can know the derivative of this function, right? So that local slope is a derivative, right? So we can calculate d j omega d with respect to W, right? I may mix up omegas and W's. I think these are, we'll try to make all those W's for weights. And so here our slope is positive. So let's move in kind of the negative direction at some proportion to that slope, okay? If that's a steep slope, we'll move a lot. If it's a shallow slope, we'll move less. But that's also going to be scaled by some learning rate, okay? Because we're just getting a slope here. We don't, it's not an answer to stick us right at that local minima where that cost is lowest. So we're going to move some distance, and then we're going to do it all over again, right? But now our weight has been updated, right? So when we go through and do our forward propagation, and we put in all of our different training set examples, and we predict our outputs, and then we compare those using that crazy complicated loss function, and then sum them all up and divide by m to get our cost function, then we're maybe going to be right here, right? And now we do it again, where we update those weights, and we keep moving. And as we move, hopefully our slope gets lower and lower. And so we're iterating into the local minima. If we go too far, then our slope turns around, right? And then we'll get pushed back this direction. So suppose with some other random initialization of parameters, we ended up over here on our cost function versus our W here. And so now we're going to have a negative slope. So we're going to move in the positive direction, right? So we're moving in a direction away from the value that the derivative gives us. And again, if we overshoot here a little bit, then our slope will change from negative to positive, and we'll kind of zero in on this local minima of the cost. right? So we're trying to minimize the cost. And as we get closer to it, the slope is getting shallower in this case, and in this convex type of situation here. And note that this in one dimension, it's kind of trivial, but this is a convex curve. If you forgive my messy drawing type thing. So if we go from any one point to another point on this curve, we're always kind of inside it, right? So, but we're going to eventually settle out at this local minima, or in this case, the global minima of this cost function. Exactly how close we get to it is kind of a function of how hard we want to work at it, right? And also a little bit of this learning rate. If our learning rate's really big, we might take too big of steps here, and we might bounce back and forth here and have some trouble converging. But if our learning rate's really small, then we're just going to make tiny steps, and it's going to take us forever to converge. So now in real life, these things are we're actually looking at both weights and balance biases, and there's lots of these things, right? So we're really talking about partial derivatives, but we're going to have an update equation here. So this little colon with an equal sign is indicating an update type of algorithm. So we're going to take our existing or our prior weights, and we're going to now take this cost function and take that partial derivative with respect to our weights, and that's going to give us a value, and we're going to multiply that by this learning rate and update our weights. Okay, and we're going to do the same for the biases, right? So all these different partial derivatives, updating each of the weights and each of the biases, right? So this is that gradient descent algorithm. So again, this alpha is the learning rate, which is determines how much of the correction is applied at each step. Too big, and the steps may overshoot, have convergence problems. And too small, as I said, may take excessive time to converge. All right, so now we're ready to talk about backpropagation. Right? So now we work so we've done some forward propagation. So we provide all these different inputs for all these different trials, and we calculate this network. Right? So we'll calculate the output of this neuron, the output of this one, the output of that one, and then we'll move on to this layer and calculate all these, and then move on to this one and we'll calculate all these, and then ultimately provide some outputs. And so you can see that we're doing a lot of repeated calculations here, which if you're interested in parallel programming, you can maybe start to see how and why GPUs are so popular in machine learning, because GPUs have hundreds or thousands of cores in them compared to maybe 4 or 8 cores in a fancy CPU. Now you've got lots of different cores that are designed to do the same calculation but on lots of different data, and that's what we're doing here. Is when you look at this, we're kind of doing the same type of calculation over and over again, but with different data, and GPUs just shine at that. So now we've done this forward propagation. We have some predicted outputs. We compare those to our objective outputs, our labeled outputs, and we look at the loss functions and then calculate that cost function. And now we calculate derivatives of the cost function with respect to all these different weights and biases, and we kind of move from this end back towards the beginning, and we update these weights, all these weights, and the biases that aren't shown here, and then we kind of step through here and calculate all these, right? Oops. So remember, these are nonlinear functions here and stuff, but we know the derivatives there, so we can propagate the values. So it's kind of like doing an inverse function, right? So if this was, instead of being this fancy neural network, it was just a sine function. Well, we would be taking the arc sine or the inverse sine as we're going this direction, right? So we're trying to look at the inputs given an output and work our way backwards and adjusting all of these things to ultimately to minimize that, but doing it in an iterative way. Okay, so all right, I know that's super high level. We'll get a little bit deeper as we start to look at specific examples of these. We're going to kind of zero in on convolutional neural networks, which are very popular in computer vision algorithms, because they, to the best of our knowledge, they do kind of mimic how our eyes work with our brain and that type of thing. Lots of different models these days. Transformers are a super popular model right now. So lots of different applications, but these same concepts are working in this back propagation, needing these derivatives, looking at these loss functions and cost functions and that type of thing, right? So, all right, so let's now kind of step off of that high level outline of neural nets and start to look at Python a little bit. And so Python is, well, maybe I'm overstretching it with saying the dominant language for applied machine learning, but it is a dominant language for machine learning. Maybe I can get away with that there. CUDA is a framework library that's provided by NVIDIA that is designed to facilitate easy parallelization of workloads onto GPUs. And so it's designed for their GPUs and other, you know, NVIDIA is dominant in the market, but there are some others out there and they have their own libraries. But if you've heard of CUDA, then that's kind of being used underneath the covers of these Python libraries, right? So you might write your application in Python, but inside, deep down below that Python code, there is calling some C++ code that then is also maybe implementing some CUDA library calls. And that would be moving data from main memory into GPU memory and dispatching workloads on those GPU cores. So, so just be aware that that is running underneath the covers. If you download TensorFlow, for example, or PyTorch for your work on your machine, then you'll want to know whether your if you have a GPU on your computer that supports CUDA, and then you can install or have it install the CUDA implementations, the low-level implementations, and it's going to run much faster. But these libraries will also just run on the CPU if you don't have a GPU of the right type that you can take advantage of. So runtime inference is sometimes developed in C++ or some similar language. There's amazing variety of things that people have done, but there's just so much gravity towards Python. And because much of what is running underneath the covers is in C++, even Python code runs really fast. But there are some apps that are written right in C++. There's actually some that are written in a hardware definition language like Verilog or VHDL or maybe System C or something like that. And you're running these algorithms, machine learning algorithms on FPGA. So that's certainly possible and definitely done. But most practitioners are working in Python at some level. So, and here's just another statement. Don't panic. Python can be a very sophisticated language. It's kind of designed to make it easy to learn, but if you've done a lot of other programming, Python definitely does things differently. And we talk about kind of thinking Pythonic in a Pythonic way, right? So, so it can have some unusual idioms in its programming, but we're going to rely on the machine learning frameworks to do most of that fancy stuff underneath the covers. So we're going to be working at a very applied level. So we're not going to, spend a lot of time looking at some of those weird things. So Python as a language has all the normal stuff you might expect out of a language. By this time, you guys have certainly learned C++ and C and maybe a handful of other languages. So, and I'm sure a bunch of you are already experts in Python. But I know from that survey we did, skills survey we did on the first class session, that some of you all haven't seen it. So I'm well aware of that. Again, don't panic. But it has if statements, and match statements are equivalent to switch statements in C or C++, and it has the ability to do functions. The declaration and calling syntax is a little different, but it's all the standard type of programming things are there. So we'll walk you through. But one of the things about Python, a number of other languages also, but Python in particular has all these different packages, and a lot of them are open source and or at least free to use, if not free to modify. And so you can access these as libraries, or in Python world we call them packages. So NumPy or NumPy, however you want to pronounce it, does a lot of numerical type things, right? So it's kind of like, all right, Python does all sorts of stuff, but for us engineers and scientists and mathematicians, we want to do lots of fancy numerical calculations and algorithms, and you're very likely going to be using NumPy. And pandas is common with data scientists and data analysts and in machine learning, and that what it does facilitates organizing your data into matrices and arrays and tensors and that type of thing. So it holds your data in Panda data frames and then operates on those data using matrix multiplications and that type of thing, right? So very common to leverage those. Scikit, actually it should be scikit-learn. And let me just update that here real quick. So scikit-learn has a lot of machine learning algorithms built into it. Oh, there's another mistake. Matplotlib, not matlib, but matplotlib is a library and the most famous component of that is PyPlot, being able to generate really nice plots, that type of thing. Kind of like MATLAB. You guys have probably used MATLAB, and you can do all your calculations, but then another big feature of MATLAB is its charting capabilities and stuff. So matplotlib is trying to do the same thing in the Python world. Then we get down to actual frameworks. There's lots more than what I've just listed here, but these are the ones that in my practice, me and my colleagues have used a lot, right? So there's TensorFlow. Let's see if I get this right. I might get it wrong. TensorFlow comes out of Google, and Keras is basically kind of an easier, friendlier way of building models in TensorFlow. So these two go together. I'm glossing over some stuff there because Keras can have other backends, but it's really evolved to be a friendlier API interface to TensorFlow. And then PyTorch, maybe it comes from Facebook, I think. It's going to do a lot of the same stuff that TensorFlow can do, maybe a little bit more generic, but in some cases you'll find that it's more performant. Like researchers might want to work in Keras and just be productive in programming and testing out algorithms and that type of thing, whereas people are implementing production type things that are really needing to train and infer very quickly might lean towards PyTorch, but all sorts of different opinions and preferences and that type of thing. So all right, so yeah, just kind of included this here. I did get the names right here, but if you wanted to install all these, you can do that. And yeah, do you want the commas or not? I can't remember. I always have to look that up. So, all right, then another important aspect of Python, and yes, I know we haven't even looked at the languages yet here, but we got all these different packages. You might have one project that wants to use TensorFlow, and another one that wants to use PyTorch, and another one that might want to use scikit-learn. And there may be some conflicts between versions and that type of thing. So when you work with Python quite a bit, you sometimes find it's a little frustrating trying to match up versions of different things, especially when you're leaning on using open source or other people's code and that type of thing. So virtual environments simplify a lot of this. So you can create a virtual environment and load that up with a specific set of packages, and then you can activate that environment, do your work there, and then deactivate it and activate a different environment. And that other environment might have different packages and that type of thing associated with it. And so you're working on various projects at a time or in kind of succession, but you may want to go back to things and be able to kind of repeat or update your results. Then you would want to do something like this, right? So there's a few different ways of doing it. There's VENV, a virtual environment that comes with or is integrated with the Python system, Python environment. And so I'm not describing here how to install Python or how to install VENV. It may depend upon your operating system that you prefer to work in. You'll probably be happiest doing all this work in Linux or on a Mac. Windows, you can do it, but yeah, I might have to work a little harder at it sometimes. So again, opinions may vary. So here, if we want to create a specific environment, let's say machine learning TensorFlow, right? So we do Python 3-m VNV VNV MLTF. Do I have that right? I think so. And then so that creates it, and then you can activate it by sourcing. So if you're not a Linux person, that may look a little weird, but you're basically saying to look at this file here in this path and process the statements in that file into your shell environment. And so now when you run that, it's all going to be pointing at this virtual environment. Windows, a little bit different. You're just going to execute that through a scripts thing, but then you can deactivate it. Conda, part of the Anaconda system, and that's another systems management type of thing, another approach at all of this. So you can do a conda create, dash name, here's machine learning PyTorch, and then you do conda activate that or conda deactivate that. Let's see if I have, do I still have something running here? Yeah, so here I can, let's see, do a Python 3-m VNV and you wait a little bit. Why is it so slow? Okay, now it's done. Let's do an ls-l, and here we will see that I guess it's in down here. So then we can look at this bin, and we'll see this activate.csh activate files here, and then we'll have our versions of Python, and pip is a utility that you can use to install packages and that type of thing. So all these versions, and then as we install packages, they'll get installed into this environment, and our paths will be updated, but not yet. Because if you look over here, we're still in this base environment. So what I want to do is I want to source and okay, so now I've done this activate, and we are now in this machine learning environment. Just making sure I still have everyone here. I had some weird sounds on my computer. Did I drop the connection? Can someone open up their mic and say that we're still here and connected?
We're still here.
Okay, good. There's my meeting. All right. So all right, so now we've done that. So we can do this with conda create also. Sorry about that little diversion there. And here we're going to specify a name, and we might call this one AI. Right? And so we get a little bit better feedback as Conda's running, and should work because I did this before. So okay, maybe I something up there, but you can see well, maybe that was in a different Ubuntu instance. That was the problem. So I think I installed Conda separately in a different Ubuntu instance. So maybe that's not why it's not working right now. All right, we won't waste time debugging that. So let's look at this kind of basic machine learning process as we go through this. So we're going to import our packages. We'll load up our data set, and then we'll build a model, define a loss function, choose an optimizer, compile the model, and then fit or train the model over some number of epochs or iterations while minimizing a loss in a training data set using this optimizer and using this loss function to calculate everything. And then we'll typically evaluate on a test data set. So you'll take all your data and you'll partition that into a training and a data set, and then a test data set, and sometimes a verification data set or something. And then ultimately you got to wrap it all in an application. So here's maybe how we might do this. We might import NumPy as NP, and this as statement is just saying, all right, now let's refer to all these things as all these functions in there. We'll use NP as a shorthand to get there. If you've studied a language with namespaces, this might make a little bit of sense to you. We might import TensorFlow as TF, and or we might want to import Keras from the TensorFlow library. So we do from TensorFlow import Keras, or actually we might want just the layers, or be able to refer to layers from TensorFlow.Keras import layers. So you see here, this is a bit of a namespace type of notation here. So then we want to do some plotting. We often do. We'll import matplotlib.pyplot as PLT. So I just kind of punch these in here, and you can copy and paste these into your own work. These are just very common and almost always done in this way. So, all right. So now we're going to load a data set. So we can use Keras helper functions to load well-known data sets from internet sites. The MNIST is a classic data set that is a whole set of handwritten digits. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and lots of these, and they're kind of a classic. It's somewhat of the hello world of image recognition, trying to recognize numbers out of some really messy handwriting. So, so since it's so popular and well known and used in research a lot, it's kind of a baseline comparison. This is just available out there, and so we can say TensorFlow.Keras.datasets.MNIST. So this is a function here that is in these kind of libraries, packages, whatever. We're using a namespace notation here. So you can view this as like a hierarchy. And so we're referring to MNIST, and we're going to load that into this variable here. Oh, we could also load from local storage, right? So we might have our own set of images, and we might have a path to that folder. And so we'll actually specify it there. And instead of image folder, that's going to be your path, or a variable holding your path. And then we'll have, I'm running out of time. This validation split is an option to say, all right, put 0.8 fraction of it into a training set, and the other 0.2 or whatever. Some various things, we have to look these things up, but we can process these, bring these in, and we'll have a training data set and a validation data set. It's a little bit like MATLAB here, this Python idiom. In MATLAB, if you wanted to return multiple values from a function call, you would put square brackets around them. Here, we just separate them by commas. Right? So if we didn't put comma val underscore ds, then we would only get the training data set. But by putting two of those, we'll get both of them. Right? So this function is returning at least those two different parameters. Okay, and so again, you're going to look these up and determine exactly what these are. I believe the seed is seeding a random number generator that implements this validation split between the training data set, a validation or test data set. All right, so there's two different ways of building up models and using this Keras helper function for TensorFlow. There's sequential, and we'll also briefly look at functional, but sequential's easier when you can use it, when your model allows it. So you can build this deep, possibly very deep neural network layer by layer. Right? So we tend to start with the input and work our way towards the output. Here, to be able to use the sequential model, actually, I'm just going to stop here. So real quick, hang with me. Oh yeah, my computer crashed earlier, so I don't have this up right now, but I did have homework 5 here, and this is going to be a nice little, hopefully fun design effort where you're going to take some objectives for an FMCW radar and translate that into a design, right? So I want you to fill out the values in this table. Look at all these different things here. Use the equations I put in that slide, summary slide at the end of that section of the lecture. And then also look at that data sheet. It should be on Moodle for that part. Look at that table I highlighted. Compare it to this. And yeah, discuss it. Will that chipset be able to implement all these things? And if not, what do you need to do to kind of adapt it? So again, due date next week. It's not a hard due date, but the quicker you do that, then the better we can kind of stay up. I can give you feedback and we can move on. You can get it done while it's still fresh in your mind. So this one will be graded. I think I assigned nominal 20 points to these things. All right, so that's it. And do I have that time right? I always got to make sure I'm not an hour off. I'm not quitting an hour early. So I guess that's right. And yeah, we'll see you next week. If you got any questions, hang on. I'll stop recording and I can answer some questions here. Some people